I will start, as a lot of other speakers started in this talk and in many other talks. We know today that gamma ray bursts are composed of two groups. For the lack of better terms, I will call them at the moment long and short. And traditionally, these two groups are separated by this threshold of 2 seconds between them. Although, as I'm going to show you in this talk, this 2 second separation is not very good separation, especially in the short duration, and it's depending actually on the detector that we're looking at. And therefore, long and short doesn't necessarily give you a very good terms for the two different populations that exist. We also know that the short gamma ray bursts on average are harder than the long gamma ray bursts. Here you see the hardness diagram from Batsi gamma ray burst, where this is the hardness ratio and this is the duration, and you can see that the long duration they are on average softer than on short durations. Now, what else do we know about the long gamma ray bursts apart from being softer? They are associated with star-forming galaxies, and they are within those galaxies they are observed in the most active regions usually. The short bursts, on the other hand, are harder. They are associated with a broad population of galaxies, both star-forming and non-star-forming, and very various types of various rates of star formations. And so I'm going to focus in this talk mainly on the model for the long gamma ray burst, which is known today as the collapsar model. The basic properties of these models is that the core of the star, of a massive star, collapses to form some sort of a compact object. This object emits a jet. The jet eventually breaks out of the star, and after it breaks out of the star, it accelerates, and after it accelerates enough, it starts to produce the gamma ray bursts that we observe, and these gamma ray bursts are emitted far away from the star. Now, I will address two questions that relates to this model. First of all, I will ask the question, is there an evidence for the collapsar model? Meaning that, is there an evidence that we actually have a relativistic jet that breaks out of something, of a star? And the second question is that the collapsar model doesn't really specify what's the nature of the compact object that lies in the center of the star. And I'm going to address the question, can we have any indication of what type of object we have there? So my talk is going to be composed of two subjects, as seems to be popular here. So first I'm going to I'm going to focus on the observational imprint of a jet breakout, and then I'm going to discuss some implications that we have from that on low luminosity gamma ray bursts, as Udi Nakar already mentioned, and the classifications of collapsars, of the classification of gamma ray bursts both to collapsars and to non-collapsars. And in the second part, I'm going to try to see how the breakout time that we're having can tell us something about the nature of the compact object in the star. And I'm going to talk about it in the context of two types of jet, a hydrodynamic jet versus a magnetic jet. And I'm going to try to explain to you how do we see the differences between the propagation properties of these two jets. Let's start with the observation. So within the framework of the collapsar model, what do we need in order to produce a gamma ray burst? So the most important thing is that the jet will successfully break out of the star. And so after the jet breaks out, it produces the radiation, and the radiation is emitted. And in most gamma ray burst model, this emission happens fast. So basically, the time that we observe the gamma ray burst represent the actual activity time of the engine that fueling the jet. However, as I said, this time you need to also account for the time that passed that the jet spent inside the star. So basically, the time, the prompt gamma ray burst duration time, is combined by the engine activity time minus the time it takes the jet to break out of the star. Now, if the engine stops before the jet breaks out, then the jet fails. The jet will not be able to break out. We will not see a gamma ray burst. And what we can see is possibly a low luminosity gamma ray burst, as Udi already told us. So can we quantify? Let's see if we can quantify this. Let's look at a simple scenario where we have all gamma ray bursts supposedly had a single breakout time. And we call this breakout time T break. Now, and we have some sort of distribution for engine activity time. Now, since the engine, and this is an assumption, I take it as a relatively reasonable assumption, since the engine is working at the heart of the star at distance scales which are much smaller than the distance in the star, the engine doesn't really know exactly when the jet breaks out of the star. And therefore, it is reasonable to assume that this distribution has a smooth transition between the activity times which are larger than the breakout times and activity times which are shorter than the breakout time. We expect that this distribution shouldn't change by much. And if we look at the distribution to observe, at the probability, to observe a gamma ray burst with duration T gamma, then this probability is just the probability that the engine works for a time T gamma plus T break, which is the engine activity time. Now, looking at these probabilities, they have two limits. In the limit where T gamma is much larger than T break, which you see around over here, then the probability that the engine the probability to observe a gamma ray burst with duration T gamma is just very close to the probability that the engine actually works for a time T gamma, because this is much smaller than that. In the opposite, and this is the case for a regular gamma ray burst. In the opposite case, where T gamma is much smaller than T break, then the probability to observe a gamma ray burst with duration T gamma is basically equal to the probability that the engine worked for a duration T gamma plus something very small. Now, this probability, since we don't expect the probability to change by much in the when T gamma is on the order of T break, then this probability is roughly constant, because this number is much smaller than this. This number is much smaller than this number. So this is a constant probability. If I want to plot it on a graph, then here I plot the probability to observe a gamma ray burst with duration T gamma as a function of the observed duration. So at duration which are much smaller than the typical breakout times, we expect to see a constant probability. That's a plateau. In duration which are much larger than the typical breakout time, we expect the probability to basically follow the engine activity time. And here we take this engine activity time distribution, which is a power law. And the turnover should occur at durations which are of order of the breakout time. Now, this probability is actually proportional to the duration distribution dn dt, the n gamma ray burst dt. So if I'm plotting in the duration, the probability, if I'm plotting the duration distribution of the gamma ray burst, the n dt, I should expect to see something that looks like that. In reality, at the short duration, I will remind you, we have a second population of gamma ray bursts, which are the non-collapsars, which tend to cluster in short duration. And therefore, they should obscure this plateau at short duration. So one of the prediction of the collapsar model, the prediction of a jet breaking out of a star, is that I should observe a plateau between a few seconds to the typical breakout time. Now, let's see if we see this thing in reality. So here I plot the duration distribution in Batsy gamma ray burst. Now, I want to specify and to note that what I'm plotting here is the duration distribution dn dt, and not dn d log t, as you've been seeing all around this conference, and usually this is what people are plotting. It's just a different way to look at it. Do we see a plateau? Where we do see a plateau between about 5 to about 25 seconds. It's there, but I wouldn't call it very convincing evidence. So the thing is that we can improve ourselves a little bit more. I remind you that the short gamma ray bursts are harder on average than the long gamma ray bursts. Now, if this hardness difference is in fact related with something intrinsic, with the actual difference in the progenitor, then by taking some sort of a threshold hardness and taking only the gamma ray bursts which are softer than this threshold, and if I will start to reduce this threshold, then I will basically clean my sample from mostly of these non-collapsar gamma ray bursts. And by that, reducing the fraction of the non-collapsars from my sample. And what I should observe in this situation is that the bump of the non-collapsars should be less and less prominent, and by that, increasing this plateau to shorter duration. So this is exactly what we did in this movie. Here is the threshold that we're reducing it, and you can see this is a duration distribution, and you can see that the bump gradually decreases with respect to this plateau. So the plateau become going into shorter and shorter duration until eventually we're just killed by statistics because there are too few events here. So by taking the average hardness of long gamma ray burst and taking only the events which are softer than that, I can extend this plateau from 5 seconds to about 0.5 seconds. The bump here is much less prominent. And this is a much more convincing evidence that what we see here is indeed a plateau. Do we see this plateau in other gamma ray burst satellites? The answer is yes. Here I plot the duration distribution of the 3 major GRB satellites, BATSE, SWIFT, and Fermi. They are just renormalized in order to fit in the same graph. In all this distribution, we do see a plateau between a few seconds to a few dozens of seconds. I'm going to address the lower part of the plateau soon. But the main thing here is that we observe a plateau between a few seconds to about 20 to 30 seconds, and this implies a turnover at T90s of about 40 to 50 seconds. Now, deredshift that, and you will get that the typical breakout time from this expectation lie on about 10 to 15 seconds. So these are the breakout times of the jet from the allegedly star that surrounds it. So let's discuss a little bit about implications that we can get from these results. So first of all, about a choked gamma ray burst. So the slope at log times around here, as I said before, represent the this duration distribution of the engine itself. Now, because we don't expect this distribution to change much at durations which are close to the breakout times, then by extending this slope to shorter duration, to duration which are shorter than this, typically 50 seconds, I am basically predicting the rate of event with T engines that are smaller than this T breakout, than this observed T breakout. Now again, this is the engine activity time and activity distribution, and this is the observed flux distribution. So if I will extend it to short duration, I'm basically probing T engines that are shorter than this typical T breakout. So at about T engine, which is about 0.5 of the T breakout, I'm getting that there are about 10 times more choked gamma ray burst than successful one, meaning that a gamma ray burst engine is more likely to fail than to succeed. Now, as Udi explained before, this is considered, there are many other observational properties that tells us that probably low luminosity gamma ray bursts are related to this choked event. And this gives you a very natural explanation, this thing, why the rate of the low luminosity gamma ray burst is indeed so high. And at the order of about 10 times is indeed what we get also from observational analysis of the rates of low luminosity gamma ray burst. So the second thing I want to discuss is, can we use this plateau in order to get a better classification method for gamma ray burst? So knowing that we have this plateau, we can use it to fit 2 populations of gamma ray burst. Here you can fit a population of long gamma ray burst, of collapsars, and on top of that you can fit a population of non-collapsars. Now, once I have this fit of 2 populations, what I can do is I can get ratios of the non-collapsars to the total population at each duration. And this plot gives exactly this ratio. This is the fraction of non-collapsars from the total number of gamma ray bursts at each duration. This fraction actually represents a probability function. It's a probability that the gamma ray that we observe is indeed a non-collapsar. If the probability is above 0.5, then it means that the observed gamma ray burst is more likely to be non-collapsar than collapsar. If it's lower than 0.5, then it means that it is more likely to be a collapsar. Now, if we take the probability of 0.5 at some sort of a threshold duration between what is more likely to be collapsar and more likely to be non-collapsar, you can see that this threshold is in fact changed between the satellites. BATSE, which is the hardest satellites among the group of these three satellites, have the longest threshold duration of about 3 seconds. Fermi, which observed between the softest band and the hardest band, which is more balanced, has a duration of about 2 seconds. And Swift, which is the softest one, have a threshold duration of 0.8 seconds. It means that if I take a sample from Swift and I see gamma ray bursts with duration which are longer than 0.8 seconds, these gamma ray bursts are more likely to be collapsars than non-collapsars. So if I take a sample with duration which, with all the events with duration which are shorter than 2 seconds, I am in danger of contaminating my sample with events that I think they are non-collapsars, but in fact there are these short duration collapsars. Now, this analysis, we can actually improve that by adding the information from the hardness. As I explained to you before, the short gamma ray bursts are on average harder than the long gamma ray bursts. And we can see it in the hardness sample of both Batsy, Swift, and Fermi. So what we can do is I can divide my sample into 3 subsamples: hard sample, intermediate subsample, and soft subsample. And for each of these subsamples, I can do this analysis that I did before, divide it into find a plateau in its sample, and then fit 2 population, and get probability functions. Now, over here we can see very interesting information that's coming out. In the hard Batsy sample, which is the sample of the hardest gamma ray bursts which are observed by the hardest satellites, I see that there is a non-neglectable fraction of events which are non-collapsars, and the duration can extend all the way up to almost 10 seconds. Another thing, in the soft sample of the Swift satellites, you can see that there are events with duration as low as 0.3 seconds, which are actually more likely to be collapsar than to non-collapsars. This means that this sharp separation of 2 seconds is something that one needs to be very careful when trying to classify an event as it a collapsar or a non-collapsar, because we need to take into consideration both the satellite that detected this event and the hardness, the intrinsic hardness of this event as it is observed by the satellite. So let's discuss a little bit about consistency of our result with observation and some implication that we get from that. First of all, here I'm comparing my result to an earlier study by Ido Berger from 2007 on short gamma ray bursts. These events were chosen according to this criterion of being shortened to 2 seconds. One thing that Ido Berger concluded, and you can see here, is that both the star formation rate, the specific star formation rate, and the offset within the population of short gamma ray bursts is very widely distributed. You see very large differences in star formation rate and in the offsets from the center of the galaxy. And with the question that we ask, what happens if we use our classification method on this sample? Does it change the result by much? And does our classification coincide with the galaxy types that Ido Berger is observing? So first of all, these 4 events that you see in the bottom, these are what are known as the extended emission short gamma ray bursts. On this, we don't have enough statistics. So we cannot include them within our analysis because we don't really know what they are. And our analysis, which is based on statistics in large enough number of events, cannot account for this. So we take them out of our analysis, and we are left with about 8 events. 2 of them are more likely to be collapsars according to our analysis. 2 of them are inconclusive, and 4 of them are non-collapsars. So first of all, you can see that both the conclusion about the star formation rate and about the offset doesn't change very much. A wide distribution, the fact that non-collapsars have a wide distribution of star formation rate, offset, and galaxy type doesn't change by much. If we take away what we think to be more likely to be collapsars. But an interesting thing that happened, I want to draw your attention to this gamma ray burst, this 051221A. To date, this is the only event that show clear and undisputable jet break. All other events that are claimed to show jet break in the short gamma ray burst, it will be, but I think that the fact that they have non-wavelength dependent break in the same regime is something that you can still argue about. But this is the only one where you have a clear and undistributable jet break, and we find that to be more likely to be actually a short duration collapsar than a non-collapsar. You can see that it is occurring in a moderately high star formation rate galaxy and offsets which are relatively low, and also the metallicity within the galaxy can be either high or low depending on on what method you're doing. So the metallicity is inconclusive. So a second thing that we put our model into a test is that in a study that was done by Wandermal and Piran lately, and what basically they did is that they took a population of 18 short gamma ray bursts according to the classification of T90 smaller than 2 seconds, and they fitted a delay function to that, to this sample. And they allow their delay function to be only a single delay or a bimodal delay. And what they found is that within the complete sample of this 18 short gamma ray bursts, they found that the best fit, in fact, combined of two delay functions. One long delay function with time of between 3 to 4 gigayears, and this combined of at least something like 0.7 of their sample, and another 30% of their sample were fitted by a short delay function, which is shorter than 100 megayears. And with their resolution, they couldn't know exactly how, but they can be certain that it is shorter than 100 megayears. Now, if you apply our classification method of this sample, then you are left with about something like 10 or 9 short gamma ray bursts. And when you try to fit a delay function for this clean sample, they found that the best fit actually combined of a single delay function, which is about 3.5 gigayears. So they, by cleaning out the samples, their delay function collapsed from a bimodal delay function to a single delay function, which is long. Another interesting implication from our study is that if you look at the complete sample of short gamma ray bursts with confirmed redshift, and you look at the redshift, how the redshift are distributed among collapsars and non-collapsars. So here I plotted the redshift of all the short gamma ray bursts that we know of today, and above here are the ones that are more likely to be collapsars. And down here, below 0.5, are the ones that are likely to be collapsars. You can see that all three events that we know of today with redshift, which is larger than 1, are more likely, in fact, to be collapsars than non-collapsars. So the claim that there are non-collapsars at redshift higher than 1 is at least questionable and should be taken with a little bit more care. And last, there is a nice anecdote that I would like to refer, which is related to the talk of Vladimir on integral. There has been a question why the integral satellites, the IBIS detector, see a very small amount of short gamma ray bursts. Actually, the total number of short gamma of events that it sees was only 5. And the thing is that integral satellite, the IBIS detector, trigger a gamma ray burst, although it's a very wide, has a very wide window of energy through which it's observed. The triggering of the gamma ray burst is done according to inside a window of between 20 to 200 kiloparsec, which is very similar to the window of Swift. Kilovolts. KeV. Yes, sorry. Between 20 to 200 keV. And this is very similar to the observational window of Swift. So if our analysis is indeed correct, and we claim that the distribution that you observe is very highly satellite dependent, we should expect that the duration distribution of integral will be very similar to the duration distribution of BATSI. Of Swift. So here I plot the duration distribution of BATSI dn dt, and below I plot the duration distribution of integral. This is actually was done over a sample that was supplied to me by Željka Božnjak. And on top of that, I plotted the duration distribution of Swift, where I just normalized it according to the relative number of events, because Swift see much more events than integral. You can see how closely they match, and you can see how closely the 5 events that you see sits within the duration distribution of Swift. So my conclusion is that it is not surprising that integral actually sees only 5 events here. It perfectly sits within the total number of events that integral sees so far, and within the distribution that we expect that integral will see. So the fact that integral has a soft triggering implies that the duration distribution is indeed very similar to Swift, as was expected. So at the end of the first part of this talk, the message that I want you to take from here is that GRB classification is in fact satellite dependent. And it's not only satellite dependent, it's involved both the duration and the hardness of the gamma ray burst. And in order to do to take a sample and to do a good classification on this sample, you also need to know exactly in what window does the triggering was made. An interesting comment made by Vladimir in a talk that we made before is that in integral, actually the triggering is something that is relatively flexible. And in principle, it can change. You can take this, window of triggering and you can move it to harder energy. But if this is done and you take the complete sample of the integral, then the classification should be done very, very carefully, and it should depend on the actual window where the triggering was made according to. No, up until now, everything was done on this window. I'm talking that it may in principle be changed, and if it does, you, as someone who wants to analyze the result, should know that, because it is important to the ratio between the non-collapsars and collapsars that you will observe. Okay, the second part of my talk, I want to address the question, can the jet breakout time reveal the nature of the central engine that power collapsar gamma ray burst? And I'm going to, as I said, I'm going to discuss 2 types of jet, magnetic and hydrodynamic, and I'm going to refer to 2 types of engine. What is called as magnetar-driven jet, which is basically an isolated magnetar, fast-spinning magnetar that is put in the center of the star and emitted jet. This is presumably emitting a very clean magnetic jet. And an accretion-dominated jets, which emits jets that can be hydrodynamic dominated, can be magnetic dominated. It's depending on your favorable model. So let's start by, I will start by describing to you how does a hydrodynamic jet propagate in the medium, and then I will compare it to the propagation of the magnetic jet. So when a hydrodynamic jet propagates in the medium, it pushes the material in front of it, and it forms 2 shocks, forward and a reverse shock. Matter that stream in the jet, the matter here is moderately relativistic, stream through the reverse shock, slow down, heated, and then it is pushed sideways into this cocoon. Now this cocoon applies pressure on the jet and it collimates it. So because of the jet is supersonic, this collimation is done through a structure of oblique shock that is formed in the base of the jet, and these are known as collimation shock. Now, the pressure inside this cocoon is roughly uniform, and therefore the width of the jet is basically the width of the jet as it is determined in this in the region where these collimation shocks are occurring, and until the jet shocks here and then streams sideways into the cocoon. So the width of the jet is in fact set around here. So what we did is we constructed a model. And before I will describe you the model, this is the 4 main features of our model are these collimation shocks, the jet itself, the head, and the cocoon. So here I'm going to plot this schematic jet over a result from a hydrodynamic simulation. And it was not my simulation. This simulation was done by by Morsoni et al. From 2007. And here you can see this structure, this collimation shock. you can see this jet, the low density jet, you can see the head, and you can see the cocoon. Now, we constructed a rather simplified model of that where we model this cocoon as a rectangular cocoon with a constant pressure. And what our model is doing is taking the luminosity of the jet, the injection angle of the jet, the medium density, and the output is the cocoon pressure, the cocoon side, the head velocity, which is going to be important for our discussion, the jet cross-section, and the Lorentz factor, and how each of these things changes with time as the jet propagates in the star. So to test our model, we compare it against several numerical simulations by several groups, not just only one group. This is a numerical simulation by Mizuta and Alloy from 2009. Here they injected a jet with a luminosity of about 10 to the 51 erg per second into the star. What you can see here is the density structure of the star in two different color scheme. Here you can see this inner region up to the red. This is roughly the jet. This is the cocoon, which is combined of an inner cocoon and an outer cocoon. And these are the collimation shocks around here. Now, on top of this simulation, I'm going to plot the results from our model. So this is the jet from our model. Here are the collimation shock, and this is the cocoon. And this is the head of the jet after about 1 second in the simulation, which is the time that they are using. I'm using here the exact same stellar structure, luminosity, and injection angle as Mizuta and Alloy used, and this is my analytic result. So it's pretty much, you have to agree that there's quite a good agreement between our simulation and their result, and our result and their simulation. A second simulation that I looked at was made by Zhang et al. From 2004. Zhang injected a jet with different luminosity into a star and he investigated the breakout time, the time where the jet exits the star. So these times for different luminosity, you can see the times that he got, and this is the total energy that the jet injected into the cocoon. So this is the simulation result, and this is our analytic result. Again, using the exact same initial condition and boundary condition that Zhang used. And this is our, you can see that the times, again, have a pretty good, are within a pretty good agreement. So after doing that, we can start to investigate exactly what does this breakout, what does this minimal activity time of the engine means. How can a jet not break out of the star? So here I show schematically what is happening when a jet propagates in the star. The head moves slower than the jet material, and therefore matter streams inside the jet and is dissipated in the head and is pushed sideways into the cocoon, and then it applies pressure on the jet. Now, in order to propagate, this head needs to be continuously pushed by the jet material from below to provide it the inertia that it needs, the energy that it needs in order to propagate. Now, this means that if the engine stops before an altitude which is the radius of the star times 1 minus beta, the jet will fail. Why does this 1 minus beta parameter is here? Because from the time that the jet stops, that the engine stops, until the head feels it, you need to account for the motion, motion at the speed of light of the material from the foot of the jet. It takes time from the time that the engine actually stops until all this funnel is actually evacuated. Now, if the engine stops when the head of the jet is at altitude lower than this, what will happen is that this funnel will be evacuated from pressure and the jet will collapse. And we will be left with only a cocoon of non-relativistic material. Now, this cocoon will continue to expand under its own pressure, but when it will break out, we will not have any light relativistic material that can accelerate and give us the gamma ray burst. What we will witness is that we will witness a shock breakout. And this shock breakout, as Udi already showed us, gives something different than a regular gamma ray burst. So this altitude of, this critical altitude of R times 1 minus beta can be translated into a minimal engine work time that leads to a jet breakout. So the minimal engine work time that leads to a jet breakout is in fact R divided by beta times 1 minus beta. Now, in a hydrodynamic jet, the head of the jet is not very much relativistic. It's the beta parameters, I don't know, 0.6, something like that. So this value is something on the order of a half or something like that. So we need the jet to stop at about half of the star in order to prevent a breakout. If I plug a reasonable collapsar number into this expression, what I get is that for a jet with isotropic equivalent luminosity of 10 to the 51 ergs, an opening angle of about 10 degrees, which is roughly the angles that we see in gamma ray burst, stellar mass of 15 solar mass and stellar radius of about 5 solar radii, the minimum activity times, which are termed as T breakout, is about 15 seconds. So this is what happened in a hydrodynamic jet. How does hydrodynamic jet differ from magnetic jet? Well, first of all, in magnetic jet, and I'm talking now only on highly magnetized jet, on jet with very high sigma value, shocks in these jets are very weak. And basically, they cannot affect much the speed of the flow. But still, we need to get into a situation where the relativistic motion here matches its velocity to the relatively slow velocity of the cocoon material around here. So we need to have a deceleration in the jet as the material approaches the head. If we cannot do it through shock, we need a different mechanism to do that. And in fact, the mechanism that does that is actually changing the cross-section of the jet. In a velocity that is supersonic, if we change the cross-section of the jet and the jet becomes narrower and narrower, the velocity, in fact, decelerates. Like if you want, in an opposite Bernoulli tube, where this is the exact opposite happened in a Bernoulli tube, that the velocity accelerates toward the nozzle when it is subsonic, and above the nozzle it continues to accelerate in a gradually open cross-section because it becomes supersonic. If you reverse it, the fluid will decelerate as the cross-section becomes narrower. In fact, the typical head, the typical width of the head of these types of jet, are on the order of the light cylinder radius at the base of the jet. At this width, the velocity of the jet roughly matches the velocity of the cocoon. Now, these widths are typically much narrower than this width of the head in the hydrodynamic jet. So the conclusion from that is that this type of a jet will propagate much easier inside the star, and it will develop higher velocities. So again, we constructed a model. This time our analytic models was a little bit more elaborated from the hydrodynamic model, because we needed to account now for the fact that the pressure does changes. We couldn't use a model with a constant change because we basically need the width of the jet, the width of the head of the jet, in order to calculate the propagation. So our model took account for the fact that the cocoon is not rectangular and there is a pressure change in the model, and we built our analytic model, and then we also run simulation. So here I show you a snapshot of a simulation of a magnetic jet simulation that I'm running currently together with Sasa Chekolstoy. And what you see here is that the density profile of the magnetic jet as it propagates inside a star with a density profile of rho going like z to the minus 2.5. It is very hard to see, I'm sorry about that, but this very thin line is our analytic estimation of the cocoon shape. And this red line, which is also very, it's a little bit weak. Yes, I know. This is how it tracks the width of the jet.
So this is axis symmetry?
This is axis symmetry. Yes, it's two-dimensional, it is axis symmetry.
And with magnetic field?
What?
And with magnetic field?
Yes, the sigma parameter, we injected a jet with a sigma value of 50.
About what?
50. 50.
And what is the helicity of the field? What's the helicity of the...
So you mean what is the light cylinder of the field?
No, B phi over BZ.
It changes with the, it changes along the jet, and it changes according to the, what we did is actually, we didn't inject a jet. We put a fastly spinning object, a neutron star or something, with a poloidal field in the center of the star, and we just started to spin the poloidal field. What we're doing is we try to simulate some sort of a magnetar.
And how do you release matter?
So we don't release matter.
So yeah, Vz
What
initially
happens
is zero,
is
right?
that as the field starts to spin, it builds up pressure because you're building toroidal field. And this pressure, because it is the symmetry of this pressure is cylindrical symmetry, so it naturally gives you a pressure gradient that decreases toward the center, and this naturally gives you a collimation mechanism.
Yeah, so it's out of radial force equilibrium initially, right?
Out of
radial force equilibrium.
Yes.
Radially non-equilibrium pressure.
Yes. Yes. But in order to provide this collimation, you do need the support from the medium. If I didn't have medium, the jet would not be collimated by itself.
Yes, and it might even be visible there, this oscillatory behavior on exit.
So you see it here?
No, it's not a constant. First of all, this is not a constant medium. Density varies as r to the minus.
The density in the medium decreases. So the jet accelerates. But you do see the wiggles. The wiggles are actually the size of the wiggles, and this is something that we analyze roughly in the paper that we are writing now. The size of the wiggle is basically determined by the location where your collimation is started, by the amount of pressure, of supporting pressure from the outside. If the pressure is high enough and the collimation is started at a location where the jet is still roughly in causal contact, then this wiggle will be roughly small. If the collimation starts at a large radii, like in pulsar wind nebula, then the wiggles can be very, very big, and then they can also affect the propagation of the jet. At the parameter regime of a star, these wiggles are relatively small, and they do not affect much the propagation velocity of the jet.
So where is the contact again? Contact.
So you have two contacts. This is the contact between the magnetic part of the cocoon and the non-magnetic part of the
cocoon. So the cocoon is magnetized.
Half of the cocoon is magnetized and half of the cocoon is not magnetized.
So going back to your previous...
The pressure, I just want to make another comment. It doesn't matter in terms of pressure. The pressure is the same pressure. Over here, most of the pressure is supplied by the magnetic field. Total pressure. And this is what I care about. I care about only of the total pressure. The total pressure is provided mainly by magnetic field here. The total pressure here is mainly regular pressure, thermal pressure, This cocoon is halfly magnetized, halfly non-magnetized.
Just a second. Then you don't really need, it's true that there is a structure, but you have a solution for a magnetically focused jet where you can still assume roughly cylinder, and it gives you, you can solve it. There is a solution.
Yeah, but the width over here and the width over here are different. The width of the jet at the wide point, at the middle of the jet, and the width of the head, which gives you the velocity, are different. You need to account for the pressure profile over here to get a good estimation about the jet velocity here. Otherwise, the jet will be slower than what it really is. This is my point. Because your jet is like a needle. So if you chop the head of the needle, then it will propagate slower than if you account for the fact that you have a sharp head. In this situation, the jet becomes relativistic deep in the star. And it crosses the star at a time which is roughly comparable to the light crossing time of the star. So the minimal activity time in this case, actually you need to account for this parameter, and this it's going to give a very large correction. And you can estimate that as roughly the size of the jet, the light crossing time of the jet, divided by gamma squared. Now, if we plug numbers into that and do the calculation properly, what we get is that the minimal activity time of an engine that launches a highly magnetized jet is much smaller on similar stars than the stars in the hydrodynamic jet. It's on the order of about 2 seconds, 1.8 seconds, in a jet with a similar isotropic equivalent luminosity of 10 to the 51 ergs per second and stellar mass of 10 to the 15 solar masses. Here I'm using a light cylinder of 5 times 10 to the 7 centimeters. So to give a short conclusion, these are the typical breakout times that infer from a hydrodynamic jet, and here I'm going to show you the typical breakout times on top of a simulation on a movie that we ran of this jet. You can see that this jet is very sharp at the edge of it, and it propagates. Here are the wiggles that, that Maurice talked about. And this jet propagate, it will exit the star after about 5 seconds, but the breakout time, the minimal activity time of the engine is about 1 order of magnitude shorter than the minimal activity time in a hydrodynamic jet. And now I'm going to do the connection to the first part of my talk. I'm going to remind you that the breakout time that were inferred from observations were on the order of 10 to 15 seconds. So the conclusion that I make from this is that in a collapsar model, hydrodynamic jets are favorable over magnetic jets. Now, it doesn't mean that the jet over here is launched as hydrodynamic, but something needs to happen and change this jet from a magnetic to a hydrodynamic. Otherwise, it's going to be very hard to stop this jet from breaking out of the star. And if you agree to my to the estimation of the typical turnover of about 10 to 15 seconds, then it means that you need to come out with a jet that it is actually stoppable. And this, I think, is hard within a highly magnetized jet.
No, I have a comment on that too.
So let me finish the conclusion, and then within the talk, within the question parts, we can discuss, we can address it. So jet breakout times imply flat distribution up to T break. The T breakout that if T engine is smaller than the T breakout, then the jet fails, and we observe a low luminosity gamma ray burst. The rate of low luminosity gamma ray is much higher than normal gamma ray burst. A plateau in the distribution can be used to derive a reliable method for classify short duration collapsars and non-collapsars. The threshold duration, and this is the message that I want you to take from this first part of the talk. The threshold duration in the case where we don't use the hardness information, at least in Swift, the threshold duration are about 0.8 seconds. These are not the 2 seconds that people usually use. If you want to do a better job, you can also use the hardness information, and then there is a whole, all these plots appear in the paper that is already out. Now, in the second part of the talk, I talked about the hydrodynamic versus magnetic jet. The typical breakout times that are inferred from observations are about 10 to 15 seconds. These times, according to my understanding and according to our model, they infer hydrodynamic jets over magnetic jet. Now, this is a speculative part, and I don't take responsibility for it, but I think it's roughly pictured the idea. If accretion-driven jet can have low magnetization, then accreting compact objects are favorable over isolated magnetars as collapsar engine. And again, I only simulated up to now jets that are coming from highly magnetized neutron star. We, in fact, going to try to see if we can simulate also jet from accretion driven flow and see if the result will be much different. So thank you very much.